Okay, so today we're going to be doing the Ideal Rankine cycle. It's the SUNY new Paltz worksheet. So, just going to comment Ideal Rankine cycle. Oops. Then there's 4 states, so I'm just going to comment in the 4 states so I can organize my code. Okay. Now I'm going to look at the givens. So at state 2, the boiler entry, we have 4 megapascals for the pressure. Oh, sorry. State 2. P2 equals, and then I'm going to do it in kilopascals because that's what E's automatically sets the units to unless you change that. So if I just do 4,000, it's going to recognize as kilopascals, but I'm also just going to define the units. Then state 3, we have 2 values. We have P3 equals, again, 4,000 kilopascals. We have T3 equals 800 degrees Celsius. We have state 4, the turbine exit, P4 equals 100 kilopascals. And state 1, the condenser exit, we have 2 values. P1 equals 100 kilopascals. The quality is 0. And we'll comment in that it's a saturated liquid, so you know why the quality is 0. Okay, so that's all our givens. And here's what we need to compute, as well as all the thermophysical properties. So again, from basic thermodynamics, once you have 2 independent properties at a state, you can find the rest of them. So at state 1 we have 2, and at state 3 we have 2. So we can use the E's functions to compute the rest. Options, function info, thermophysical properties, real fluids, because we're not using the ideal gas assumption because we're using steam. Specify steam as your working fluid. Then you want to choose real thermal props. You could individually find like enthalpy, temperature, pressure, specific volume, using all individual functions, but this just really simplifies it into one line of code. So our independent properties are pressure and quality, so we must define that. Paste. Again, this colon separates our input variables from our output variables. So these 3 are our input variables, our working fluid, and then our 2 independent thermophysical properties, and here are our output variables. And again, since we already know the pressure and quality, you could delete these, but I'm just going to leave them. And then again, here's the function that E's is calling. It's a function that E's has automatically in its system. So I'll specify independent properties, the input properties. Here's the output of the function, T1, P1, V1, H1, S1, U1, X1. If you don't want to find all of them, you could just delete them. And also, important note is that E's does not recognize lowercase and capital letters. So here we have X1 lowercase. Here, let me just specify that. We have X1 capital, because here we have X1. So it's not going to make a difference if it's lowercase or capital. Then if we were to hit calculate solve, we would find all of them, but I'm not going to do that yet. We'll do state 3. Options, function info, thermophysical properties, real fluids, steam, real thermal props. Then we have pressure and quality. Paste. Oh, sorry, we have temperature. So I don't need to redo that. I can just get rid of this quality and write T equals, and then I'll do T3. So yeah, if you make a mistake like that, you don't have to delete this whole line of code and redo that entire process. can just type it in. Okay, so now we'll know all of state 3 if we were to solve this. Now we need one more value to solve state 2, one more value to solve all of state 4. So if we look at the ideal Rankine cycle, what do we know? We know that the pump and the turbine are isentropic. So here, that means for pump, the entropy at state 1 equals specific entropy at state 2. So again, found state 1 here, so we know state 2. So we'll do S2 equals S1. Now we can do real thermal props. We have pressure and entropy. Paste. State 2. That. Okay. And then state 4, we look at our diagram, we see state 3 to state 4, it's isentropic turbine, so we know S4 equals S3, and we found S3 here. Oops. S3. Now we can do options, function info, thermophysical properties, real fluid, steam, real thermal props. We have pressure and entropy. Paste. 4, P4, okay. Now if I were to solve, we would have our entire array table. But let's just find the entropy values now. So I'll just comment here. Oh, sorry, not entropy, energy. Energy values. Now, we need to know the mass flow rate. I believe it specifies this somewhere. Okay, I guess you don't need to know the mass flow rate for this. So we'll find specific energy values. Okay, so we'll do lowercase t. So specific work from the turbine is H3 minus H4. Specific work of the pump, or we'll do B. So heat supplied to the boiler, that's Q in equals H3 minus H2. Then we have heat wasted by compressor, so that's heat out, specific heat out. And we have H4 minus H1. Then we have specific work by the pump. That's going to be H2 minus H1. Then we can calculate efficiency. And that will be eta equals work of the turbine minus work of the pump divided by the heat into the system times 100. Now that means we've found everything once we hit solve, so I'm just going to maximize this. I'm going to hit calculate, solve, and hope there's no errors. This equation does not have an equal sign. Okay, so I put an equal sign. There we go. Okay, expand our array table that we created. We have the 4 states. T is mixed. You can right click this, specify your units. So I'm going to specify degrees Celsius. It's probably a good idea to do. So entropy, kilojoules per kilogram. Here, kilojoules per kilogram per Kelvin times Kelvin. Okay. here we'll do meters cubed divided by kilograms. This is how you can do units for your rate table. Specific entropy, kilojoules divided by kilograms. Also, if you wanted to know their rate table T in Fahrenheit, you could do this second unit, so you can show values in alternate units. So here's what it would equal. If it was in Fahrenheit. And then here we have our efficiency is 33%. I'm just going to check that. Okay. Now what I can also show you is how to create a parametric table if we wanted to find what would happen if we changed the P max of the system. So right now we have, again, 4 megapascals or 4,000 kilopascals. Simplify this. I'm just going to make this equal to P2. I'm going to comment this out. So like if I were to calculate solve, it's not going to let me because it's underdefined now. But we want this variable underdefined for when we create a parametric table. So we're going to do tables, new parametric table, variables in the table. We can do work of the turbine and efficiency. We can add those. Okay, so here's our parametric table. I'm just going to get rid of that because we don't need that. Can right click, insert column to the left. What I'm going to do first, so I'm going to define a variable P max. I'm just going to equal it to 4,000 kilopascals. Now I'm going to solve it, so this runs through. Never mind. That. P max. Okay. Calculate solve. Oh, here we go. Okay. Now we're definitely good. So I just replaced my P2 with P max. Still shows up here. But same values, but this is for our parametric table. Because right now we have a column of efficiency, worker turbine, but I want to add the maximum pressure. So I'm going to insert column to the left, and I'm going to add this P max. So that was the whole point of that. We can rearrange this. I want efficiency to go after work of the turbine, specific work of the turbine. So corrected that. Now I can right click this, alter values. I want the first value to be 200 kilopascals, the last value to be 23,000 kilopascals, choosing linear with 10 rows. Okay, so we have that. So now we have this generated. You're going to see if we hit solve table, this is listed as table 1, so we hit OK. It doesn't work because it's already in the equations window, so it's overdefined. So we have to comment this out. Now this, calculate solve table, table 1, because it's named table 1. Now it works. I just didn't define my units, so they're saying there's unit problems. There we go. So that's how you find that. Okay, so now that we have a parametric table, I'm going to show you how we can do plots XYZ plots, or just XY plots because it's two-dimensional. New plot window, XY plot. We can name this plot. What do we want to name this? We can do max pressure versus specific work of turbine. So our x-axis will have Pmax, y-axis will have WT, and again we're doing the parametric table because remember now we have an array table from when we found the states, and now we have a parametric table. This is our parametric table. So you want to make sure you choose the right table, and if you had multiple parametric tables, choose the right table name. This is table 1. Then we can specify colors. Do symbol. Then we have our minimum and maximum values. We might need to adjust that later if you do need to. Then we can say that's how we would do an XY plot using a parametric table. I can right click this, I can save this. Cannot accidentally click. Great. Save. Can open up a Word document. Insert picture this device. God. Use Mentor. It didn't load, but that's how you would do it. Okay, I just labeled it wrong. That's how you would put this in a Word document. Okay, and that's that.